So Monica and I are going to be presenting about our journey in migrating a sort of homegrown, custom streaming feature engineering system to a Databricks-based one. And we've organized around a few different kinds of lessons we've learned along the way that we wanted to share.
Hello, my name is Monica Hristova. I'm principal software engineer at DraftKings. My areas of expertise are distributed real-time system built on top of Apache Flink, Spark, and Databricks. And my current focus at DraftKings is our internal fraud detection system and different streaming initiatives.
My name is Greg Von Pless. I'm a principal data science engineer, been with DraftKings for 5.5 years, I think. And yeah, I do the stuff that it says on there. Okay, so for anybody that hasn't heard of us, DraftKings is a fantasy sports, online sports book, iGaming, and more company, a number of verticals. And for the scope of this presentation, we're going to be talking about some of the work that we do to try to ensure that we're providing a safe and secure platform for our users to engage with our products. And so, yeah, we've got a lot of people doing a lot of stuff, especially being a sports betting platform when we have major sporting events happening. There's a lot of user actions happening. And we want to be able to try to mitigate some of these kinds of problems, payment fraud, account takeover, things like that. And for the scope of this talk, we're specifically focusing on introducing machine learning models to kind of like critical flows. So, if things take too long, it actually slows the user experience, and we don't want to have that happen. Outside of that, there's a whole lot of different things that DraftKings invests in to try to make sure we have the safest platform we can. To provide a little context before we go through all the lessons that we're going to talk through, we're going to give an overview of what the homegrown system kind of looked like and then what we've evolved it into. So I get to talk about the old stuff, and then Monica gets to talk about the new stuff. So when we first looked at building the machine learning part of all of this, it was something that we kind of had different teams working on different parts of it, and so the system we ended up with reflects that a little bit in the sense that the data scientists, I can talk, I swear, went off and built their model training pipelines and engineered their features and all this stuff and ended up with models they trained that went into our Databricks registry. And then separately, our engineering team built out the stream processing and live feature computation, all that stuff. The outcome was fine. It worked, did the thing. We were able to introduce a machine learning model live in one of these flows. But what we ended up with, highlighted on the slide here, is there's points in the system where we kind of had to manually synchronize and make sure things were being done the right way, or else we could introduce the dreaded offline-online skew, and then suddenly the performance metrics we got with offline testing didn't match exactly to what we were seeing live, and we had to keep going back and figure out why, and lots of iterations.
Yeah, so we decided to pivot, and we decided to move towards a new architecture, which was built on Databricks. The architecture ensured that each event that we actually get is processed consistently, and whenever we need, we can basically rerun the whole flow and reproduce everything. What was interesting for me was that usually when you onboard projects and systems on Databricks, you expect all the new cool technology, and your teams are going to be quite motivated about how they would work on that platform. But what it turns out is that we also needed to adjust some of the processes that we have in order to, in a way, make the teams work better on the platform. So here I have outlined a few of the most important points that we covered, and I'll just give a brief explanation, and then we're going to talk through those in the next slides. So first and most important thing, we wanted to address the problem that Greg just mentioned regarding the data skew and the different pipelines. So we decided to unify the process and introduce one single pipeline that does the same transformation, both for the batch and for the streaming data. Next, just because we, in a way, merged the work between the data scientists and the engineers, we saw that we actually had to address that problem, and we merged their backlog as well. So both teams had to work towards the same goal and achieve the work on the same platform. So the next thing that we did, we wanted to be able to use that unified pipeline in a way that it both populate the offline feature store, which is used for training and validation, and at the same time the online feature store, which is used during the serving phase. That way, we reduce the feature skew, and we have achieved basically zero feature skew. Next, in order to achieve all of that, we needed to ensure that each event that we actually get in Kafka is actually persisted into the data lake the way it was originally produced. So basically, no changes in its schema. So whenever we needed to, we could replay and backfill and come up with new features that we can use. All of this resulted in a system that was built in for replays, backtests, and it was really easy to basically backtest challenger models against the champion one on production. And this way, we were always sure that whatever we had on production it's the best model that we had. And as usually happens, when you do such a big change, new frictions pop up, and you have to work towards those. One of it was, it turned out it's not enough to merge the backlog of the data science and engineering teams. Greg's gonna talk about that one in a minute. And also, we needed to refactor parts of our event instrumentation in a way that we had to ensure that all the streams carried the right context, the context of the domains that we had. Greg?
Cool. All right. Lesson 1, save the right data. If the lesson sounds really obvious, it's just because we've done such a good analysis. So really what this is about is figuring out the data that needs to get captured so you have the right training history can be more complicated than it seems up front. And so what we started with was a bunch of existing microservice systems that some of them talk to each other through like synchronous REST calls. Some of them are talking to each other by sending events on some kind of event queue. They have their own dedicated databases. And in order to get the data that we were using for a lot of our machine learning work and data science work and things like that, our data engineering team makes sure to sort of, I like to say, scavenge the data. I think some people would call it liberate the data. But get the data out of everybody's databases through change capture. And for a lot of use cases, like this provides us everything that we need. The systems capture all of the important transactions and things in their database, and then we're able to build off of that. But for the kinds of use cases we're talking about here, some of the features that we needed to develop were, kind of like they have to be fresh, they have to be low latency, and they are, related to events that just happened somewhere in the system. And so then what we run into is sometimes the services weren't writing the events to their databases as soon as they happened. And so we didn't know in the historical data, when did this event actually get created? So now we have to start subscribing to events that they're publishing and harvest those. And then we run into, between what's being written to the databases and what's being published to event queues, sometimes that didn't actually have every single thing that happened in the system. There were some things that happened that we had never had a business reason to record before, so it just didn't get saved. But then it turned out when we're trying to reconstruct what was happening to present really good training data to the model, we needed to know that stuff. So now we have to start capturing, like, when do these service-to-service calls happen? And so, yeah, the summary here is essentially when you're dealing with high freshness, low latency, and like short time windows, it's not enough to know kind of like what each service did, but you need to know exactly how the system as a whole processed it, because delays and other things inherent to the distributed system impact what did anything look like at exactly the time the model got called. The answer to this is to try to like push your engineering teams to embrace more streaming first patterns and get ahead of things and try to get them to publish and record important events so that you'll have that data before you need it. And then when you find out that you don't have it, it never hurts to have a really cool data engineering wizard around who can go. We had a guy that went and scrambled through all the data and managed to like recreate history through, I don't know, magic. It was cool.
So yeah, next lesson is how we build those unified pipelines or the unified training and inference pipelines. So in order to achieve this, we wanted to follow the Kappa style, which is like, it has proven to work. So for us, in that case, the batch is just historic stream. So basically, we can reprocess it as it should be processed if it was part of the event stream. Next, we depended a lot on the unified Spark API. So as Greg mentioned, having two different pipelines, it's really hard to implement and keep in line between the teams. But actually having this unified Spark API, it's really easy to basically make the teams work together. They share the same code reviews, the same code, so it was just easier to help each other. Next, with the fast backfills and the replay testing, we were able to do fast backtests and let's say new and emerging fraud patterns that we thought we seen. We could really fast basically reprocess them and have them surfaced and decide how to proceed from that point on. And last but not least, the developer velocity. Imagine that having two different teams working on absolutely the same requirements, but the one team working on the data that's processed as batch, and another one that's actually processing everything in real time and using totally different framework. It turned out it's really hard to actually align those teams to prove that the code bases that they had actually produce the same results, to test it twice, to have a process where you can actually be sure that the results are absolutely aligned and they don't drift too much apart. So yeah, developer velocity was, we definitely saw improvement there. And why it matters? First of all, the hardest to debug, nastiest problem in the ML systems features queue, we basically, right now we have it, it dropped to 0 for us. Next, those fast experimentation loops that I mentioned, it's really easy for us to just run the same pipeline or come up with a new pipeline with new theory and just prove it by reprocessing everything and see the results. Next, because we keep full history, so every event that we need for our fraud system, every transformation that the pipelines did, every model version, every evaluation that the model did, everything gets snapshotted into the Delta Lake. So we have all the data and we can learn from it. We can improve. So basically we can always analyze or reprocess everything and be able to see where our thresholds need to be adjusted. And this gives a lot of confidence for our internal teams because imagine our operation teams. Just a slight adjustment might affect them. And now we actually have a proof why we did that. So yeah, it's really cool that we can do that and we can have such a system. But as it usually happens, it's really nice to have unified pipelines, but they are not a silver bullet. And if you don't have the right conditions in your company, having a unified pipeline won't help you solve any problem. So if you don't keep the complete row history and if you don't have data mesh mindset, it's not going to work for you. So here I have outlined a few risks that we identified at DraftKings and how we mitigated them. First, Greg already hinted about that one, but missing or trimmed row events. So what happens? No history, features drift apart, it's not possible to do backtesting, it's not possible to replay. So what you should do? The best case scenario, keep the raw data tables forever. And if this is not possible, at least as long as your model needs to look back. If not, yeah, you have to backfill from database snapshots or object store logs or other external sources, but that process is really slow and messy. It's not ideal. Next, a lot of people and a lot of teams I have seen, they want to keep only the aggregated data in the landing tables. It sounds tidy, but it's not okay. Just because you stop the innovation of features. You can't compute new features, you can't you can't reprocess, so don't do it. If you want to, let's say, if you want to be sure that you can actually reprocess and have the same functionality for your system, just land immutable append-only source events before you do any batch, ETL, or any kind of transformation on top of the data. Next, it sounds really nice to have a centralized team who actually can implement all of your transformation pipelines, but what we notice is that when we keep that ownership in a central team, that this is not the only tasks that they have to work on. It causes delays for the domain teams, and it's really hard to keep up with what actually the business wants. So what we actually did is we embraced a little bit the data mesh mindset. So we pushed the ownership of the raw and curated tables together with the contracts and SLAs to the domain teams. And then the centralized team actually started implementing schema-agnostic pipelines that land every message as is in the lake, and we use it from there. Then the downstream curation, modeling, and contractual governance, we delegate as appropriate. It could be the centralized team or our domain teams. Next, I think we've heard a lot of lectures about that one, or presentations yesterday with governance and lineage. If you can't trust your data, just nothing works. So it's hard to prove that what you did is actually working, it's performing the way that you expect. Some audits may fail. So for us to actually enforce better governance and lineage, we had to introduce the right tooling in order to know that we have that one. So for us, it was the Unity catalogs, the schema registry for the streams, and automatic lineage capture, which we use to trace down every model evaluation down to the stream that actually, yeah, helped it. Yeah.
All right. Talk a little bit more about teams and backlogs. Yeah, so another, I guess, pain point we had run into, especially developing the first system that we talked about, was not necessarily aligning the backlogs between all of the people involved in trying to build the end-to-end streaming system. And what we end up with is, we've got the data science team over here, and they've got, this is one thing they're working on, but it's not the only thing they're working on, and then they start developing features, and then they need those features to get put into the streaming pipeline. But the people building the streaming pipeline, supporting that, that model building effort is not the only thing they're working on. And so there's a lot of, waiting that ends up happening when you're trying to get everything synced, and then there's a lot of status meetings where somebody says, what's going on with that? Oh, we're blocked by them. And then, you know, when managers hear the word blocked, their like hair goes on fire and everyone freaks out. And so as we were building this new system, something that we went out of our way to do was make sure that everybody involved in sort of implementing all the stream processing and sort of feature publishing to the online feature store, everybody working and developing what features we need and training the models. We're working off shared set of priorities, shared backlogs, so that as we needed to hand work back and forth, code reviews, validations, all this stuff, it was a lot easier to make sure that, you know, progress didn't stall. And then the other thing that happened here was, Monica's going to talk about it a little bit more, but I'm going to steal some thunder. Our streaming engineering team actually went out of their way to go learn PySpark so that they could write all of their transformations in code that was going to be easier for our data scientists to read and review and edit, which was really cool.
So yes, as you can imagine, it took us a few iterations until we got to the point where we are right now. And the original MVP started with data science having their own code, as Greg mentioned, and engineering starting working on this absolutely new and amazing project where they had to implement real-time transformations. Originally, we picked Microsoft Orleans, which is an actor-based .NET framework. And we were targeting the freshness of the features. So in other words, we wanted to be optimized for latency. And our goal was to achieve sub-second for our stateful computations. And we did. But then we decided thinking, what's next? How we want to build our platform, looking at the system holistically. And we realized that just having some features optimized for latency is not enough. And we wanted to evaluate more dimensions. I have listed the most important ones for us. And by looking at those, we realized that probably, we might need to migrate to something else. So stateful computation and latency optimization. Basically, with Orleans, we had a sub-second, while with Apache Spark, we achieved the same stateful transformation at about 2.5 seconds. It's slower, but it is still within our SLAs. But then when we come and started discussing the replay and backtesting, and we realized that it's really hard to implement it with Microsoft Orleans. It ended up with a lot of custom code and hard to test. So once we actually decided to fully migrate to Apache Spark, it was quite easier. Spark supports native functionality like watermarks or time travel with the delta table. So it was something that came out of the box for us. The next one, features queue. As mentioned before, 2 code bases, 2 teams, twice testing the same thing. And on top of it, we had to come up with a data queue monitoring process to ensure that the features never drift apart, which is quite a heavy process, and it's not fun. So with Spark, we shrunk the code to a single pipeline, which starts processing first historical data, and then it continues in real time. 0 data queue, easy as that. Next, the ecosystem and ML tooling. As you know, as you may know, Microsoft Orleans is really good framework, but it doesn't have that much of a support for the ML systems. While with Spark and Databricks, we have all the functionality that our data scientists needed, like ML flow support, feature store, hooks, everything that any data scientist would need. And then the unified batch and streaming API, it's really cool because now we can process with the same API data that we have in S3 buckets or Kafka, and you don't need to change the code. It's the same data frame operations. And last but not least, I feel like Greg has something for the .NET language, but data scientists don't like .NET. So it was easier to migrate all of our engineers to PySpark rather than doing vice versa. And as it usually happens, developers, they are always hyped about any technology, and we were quite excited about Spark, but once we actually started digging in and working with the framework, we figured out it's not perfect. It just does the work for us. So I have listed a few of the pain points that we have and some of the fixes that are headed our way. So one interesting thing was the watermark on idle streams. So as you may know, the global watermark only progresses whenever you actually have events that arrive. And even though this is not the case at DraftKings because we have quite a lot of events in our streams, sometimes it may happen that some event, there is silence for a bit. What this results in window that never gets evicted because the watermark doesn't progress, and basically your state lingers indefinitely until another event arrives. It's not a big deal, but yeah, sometimes happens. The next one is the micro-batch latency floor. With all our tests and our production systems, we just noticed that achieving a sub-second transformation with the current state of the framework, it's just not possible. But the cool thing is that Apache Spark already provides the real-time mode, and I expect that ceiling to disappear. Yesterday there was an amazing session about that one. Next one, no-state schema evolution. Imagine just doing a simple change like widening the value type of in a stateful operation. Try that, deploy on production, and you will get query fails with state schema not compatible. Our workaround right now, we usually wipe the checkpoint out, and then we start from the beginning. And yeah, we have a workaround, but with the new version of Spark, this is already addressed, and there is schema evolution. Next, what we noticed is that there is no parity of the current Spark version between the Scala API and the PySpark. And for example, people who actually use Spark with Scala, they may know that there is a way to actually provide the user-defined initial state in the Scala API by using flat map group with state or map group with state. With Python, this is not an option. So what we actually did is, or usually do, is we always start processing the data from the beginning, then we have the state, and we continue in real time. And this is, by the way, also addressed in the new Spark version, so we're quite excited. And last but not least, up to now there were no timers per key, which is something that we heavily depend on in our implementations. We have a workaround with state group timeouts, which works, but it's not ideal, and the code is a little bit complicated. But with the new transformed state API, we already have timers, and we are quite excited about it. We already tested it, and yeah, it's amazing. Okay, my last lesson is the trade-offs between having a system that's optimized for latency and a system optimized for cost on Databricks. And what we've learned. So initially, we were optimizing our system for latency, and we tried to have the same with the new Databricks/Spark implementation, and we were able to achieve a few seconds end-to-end feature freshness for both stateful and stateless pipelines. And we were quite heavily utilizing Photon clusters, which we use to optimize our persisting of data into the Delta Lake. And we managed to achieve with those jobs around a second for that persistence. But what actually happens is that it turned out Photon is quite expensive for systems that are built to run 24/7 and system with our traffic. So we had a new goal. Let's reduce 50%, the cost by 50%, and still try to keep the latency inside our SLAs. So after 3 weeks of optimizations, we actually did it. We achieved, we got our GPUs down by 78%. The underlying cloud infra was down by 70, and we still managed to keep our SLAs, but we increased the latency by 3 times. And what we actually did, first of all, we disabled Photon for all the jobs that, that you used it, which reduced the cost by 3 times and increased the latency 2.5 times. So you see it works. It's just expensive. Then we started right-sizing our instances, because before we were using beefy compute-optimized clusters, which were giving amazing performance. And then we started right-sizing them. We did a lot of horizontal scaling instead of vertically. We also downsized our driver nodes. So we tried to keep utilization no more than 80%, because if you keep it more, if you have it more, it actually increases the latency additionally. And after doing all of this, what we noticed is that for the stateless jobs, there was no latency bump, no change in the latency, while for the stateful computations, we saw between half a second and a second latency bump. And maybe you don't know, or you know, I don't know, but having simple queries just adds additional GPU cost to your build. So what we did is we merged simple queries into a single pipeline, and this additionally saved from the cost. And I know that recipe is not exciting, but what we actually did, first of all, what we actually recommend is, first of all, ensure that your code is well optimized. For us, this wasn't the case, because we involved our Databricks team since the moment we started implementing the pipeline, so our code was well optimized since the very beginning. But when you actually start testing, ensure that you start small and only scale when you see that you don't have the performance that you expect. Use Photon only when it really accelerates your aggregations, and when you actually need it. Tag and surface every cost that you have on Databricks, and do regular tune-ups whenever the data, especially when the data volumes change. Upgrade to Spark 4. This is part of our backlog already, because Spark 4 real-time mode aims for sub-second transformations. And always cooperate with your Databricks team, because they definitely know how the things work, and they're always happy to help us. And I think this is it.